It's my pleasure to join everyone today, and I hope you enjoy the webinar. As Rick mentioned, Hybridyne Power Electronics, or HPE, designs and markets high-efficiency, high-yield power electronics for PV solar applications. And there's basically an industry perception that there's little to no appreciable benefit to harvesting energy from solar arrays at times when insolation or irradiance are low. Not surprisingly, almost all inverters convert just a fraction of the available energy to a usable form, and this is evident in many of the designs that are based on 20-year-old technology. Modern power electronics, demonstrated in our double conversion approach, has given us the ability to increase the electrical yield from solar arrays by 30% or more. I think it's safe to say that everyone active in the solar power generation market shares a desire to see solar compete effectively with fossil fuel-based power generation. And before I begin to discuss the optimization of yield, I'd like to take a moment to differentiate efficacy from efficiency. Efficacy is a measure of how much of the available solar resource is converted, while efficiency is a measure of how well it performs the conversion. And it's efficacy of our existing technology that is our single greatest limiting factor, and it impacts cost or CapEx and the viability of our projects. The challenge is to harvest more energy than we do today by tapping into the energy that's available during low light periods throughout the day. So as we increase a system's efficacy, we increase its yield, and we increase profitability. So let's start by taking a look at the factors that affect the yield of a solar power system. First, there's insolation, and insolation is a measure of sun hours, and as you can see, it's determined by geography, so that the southern belt typically sees greater insolation and irradiance than the northern areas, and it's represented by a number that's expressed in kilowatts per square meter. So a baseline in any location, whether you're in the sun belt or a more northern latitude, as I am today, is effectively determined and sets the maximum that you should be able to achieve in that region. No area, or array can allow a system to gather 100% of the sun's energy, and as you know, of course, you're limited by when the sun is shining, and a typical system starts beginning to yield in mid-morning and ends in late afternoon. Another aspect to consider is the tilt angle of the panels. If we're in the northeast, as I mentioned I am, it's typical to see those panels anywhere from 30 to 45 degrees inclined, as opposed to lesser inclination as you get closer and closer to the equator. So in the southwest, you might see an installation where you'd have a potential of 10-degree inclination. And I won't get into at the moment the strategies to effectively lessen the inclination and get the panel lines closer together so that the area is more efficiently utilized, because while that conserves area, it doesn't necessarily improve the output of the panels, and that's what we're talking about, the effective yield of the systems today. And of course, choice of panels has an impact as well. By manufacturer, we see the output rating varying, and of course the cheapest is not necessarily the best, we know that for sure. And then we also have the issues of decay in the panel. As the panel gets older, typically the decay is in the neighborhood of 1 to 2% per year. Let's take a look at yield here in a little bit greater depth. We started with the term insolation, and so we have a certain amount of light available to us at a given latitude. And as you know, this is determined by the sun's rays as they hit the ground and the sun's height in the sky. So in early morning, for example, as the sun is rising, it's actually penetrating a larger cloud layer, or atmospheric layer if there are no clouds. And then, of course, we have the same condition late in the day, so that the available insolation or irradiance is peaking after mid-morning and diminishing in late afternoon before the sun begins to set. The next thing we'd like to look at is now the concept of illumination. So if we're talking about our hypothetical example here, let's assume, as you can see by the regions where we see the yellow and the orange meeting, that some clouds roll in the morning, it clears for a couple of hours in midday, and then the partial cloud cover returns for a period in the afternoon. So while the sun is just as bright above the clouds, what we see below the clouds where we've got our solar array installed is of course affected by and diminished by the clouds. So now let's look at what a typical inverter does for us. It turns on when the sun's light is sufficiently bright to cause the PV panel to generate the minimum voltage required by the inverter to wake up. It's usually 300 volts DC on a 600 volt DC max inverter, which is typical in North America. And if you look at any of the specifications across the board among inverter manufacturers, you'll find that the minimum VDC rating is approximately 300 volts, give or take 10 or 15 volts. So let's look at the graph of daily yield a little bit more closely. Point 1 is the point at which the inverter is sufficiently satisfied by voltage so that it wakes up. And again, now the shutdown is at 0.5, the opposite end of the graph. And this is where the illumination is not sufficient to allow the inverter to be on. So if we look in between, we see that there's a point at which there's a cloud cover which is sufficiently covering the area so that at point 2 the inverter effectively shuts down, and then at point 3 it's activated again as that cloud has moved by. Same thing occurs to a lesser degree at the dip at point 4, where we see that the cloud cover actually diminishes the illumination but not sufficiently to turn the inverter off. Now we're going to take a look at what an enhanced inverter can do. And because it basically requires a lower voltage threshold to start yielding power, we begin to see it operating earlier than the conventional inverter. So we notice that the enhanced inverter turns on at 0.1, and it stays on longer during the day so that it doesn't really turn off until 0.5. So it's a wider profile than the conventional inverter. So at 0.2, when those clouds rolled in and the conventional inverter shut down, we see that the enhanced inverter is actually still operating, producing power, albeit not as much as it would in a brighter period of illumination. And then as the illumination increases, both inverters are producing more and more electricity. And then during the afternoon, where we saw that peak, we're at the midpoint of the day, we're both at our highest levels. And then of course, when we've got a bit of shading in the afternoon, there's a decrease, but it's not as impactful on the enhanced inverter as it is on the conventional inverter. So in summary, what we see, if you look at the difference between the two graphs, all that area that's green is actually additional energy that is available as a result of the enhanced inverter, up to 30% more yield annually. So now that we've looked at illumination and its effects, we'd like to talk about what factor affects solar PV yield and offers the greatest opportunity for improvement. The focus has been on the solar module that creates the output, while power electronics has been at best pretty much a second level consideration. But I'd like to take a closer look at the role of the inverter. Most inverters are competing in terms of efficiency. We talked about efficacy versus efficiency earlier. And in this case of efficiency, they're generally operating at about 95% plus or minus a few points. And if you look at the curved portion of the graph above 80%, you'll see the measure of efficiency of a conventional inverter. And now let's focus on the range of the inverter's operation. In North America, most inverters wake up when that DC voltage from the streams reaches 300 volts DC, and they continue to operate up to 600 volts. But as you may have noticed, they ignore any voltage less than 300 volts, and this means they're ignoring a lot of energy. Now we can take a look at the hyperwatt inverter and see how it differs from conventional grid-tied inverters. Since the hyperwatt inverter wakes up at 90 volts instead of 300 volts, it almost doubles the range of the conventional inverter. You can see the area between the blue curve and the red curve representing this increased range. As a result, when you sum up the power converted during the periods when voltage drops below 300 volts, yield can be increased by that 30% or more that we're talking about. In terms of capacity factor, we're now looking at 17 to 19% rather than 13 to 14%. As you can imagine, it's the advanced technology that allows us to increase the yield so dramatically. The double DC to DC conversion front end of the hyperwatt inverter that allows the unit to wake up at 90 volts DC is what enables the increased yield. We like to call this utilizing the shoulders of the energy curve. And you can see this effect in the areas between the two curves on the left, early in the morning, and the right, late in the afternoon, on those two sections of the graph. And in low light conditions, such as cloud cover, of course this is extreme cloud cover shown in the middle of the graph, the conventional inverter is often off. And snowy days will have the same effect, and it's interesting to note that the lower voltage threshold of the hyperwatt inverter will actually allow the panel to warm up because it has a load in the inverter, and the snow can slide off if the angle of inclination is sufficient. So it basically creates a situation of automatic snow removal in some cases. As we look at inverters, I wanted to create a list of factors that I think are important to consider when evaluating inverters. Number one, or top on the list, is electrical yield. And this is the measure of kilowatt hours produced per kilowatt. And we are a bit unique in the industry. There are some that provide some measure of higher yield, but I think when you look at numbers in the neighborhood of 25 to 30% increase, you'll find the field to be very rarefied. So it's important to consider whether or not you want to take advantage of that yield in your project. Certainly inverter lifespan is an issue, and the warranty associated with that inverter. Typically conventional inverters have a life of about 10 years, and to the extent that you may be able to secure a warranty for more than 10 years, you're still expecting to replace that inverter in about the 10-year point. The hyperwatt inverters actually has a 200,000 hour rated life, which is actually 40 years, so we fully expect to see the inverter living very comfortably through a 20-year project, and if it carries a 20-year warranty, it's not a situation where it's being replaced. Modularity, I think, is an important point to consider when you consider the speed at which you can repair or replace a component of an inverter. We have one series that we call our modular series, which is based on 12 kW power modules. You'll see those in a drawing coming up shortly, and it allows the module to be replaced very, very quickly from the perspective of a repair. Indoor versus outdoor installation is a consideration. There's been some good papers written that talk about the increased rate of degradation of inverters as a function of being installed outdoors and dealing with those climatic conditions as opposed to being indoors. So certainly something to look at if you have the opportunity to place an inverter indoors. One of the principal problems with an outdoor installation is the amount of condensation that occurs inside the cabinet with the relative humidity that's present and the damage that this has on electronics over time. That, coupled with high and low ambient temperature, can increase the dust inside the unit, and also if the temperature is low enough, as in very, very cold areas, then starting up the inverter is not advised when you're below the rated operating temperature of the electronics. One point that is often overlooked is preventive maintenance, and we find it very common that folks are totally ignoring preventive maintenance on their inverters, and it's very, very, very important to look at the replacement of filters and periodic review of the inverter and its capacitors and certain elements to know that you're not looking at the potential for unexpected downtime as a result of ignoring PM. And the last point is an isolation transformer, which I'll talk about in a little bit. I mentioned some of these things when we were just looking at the overview of points to consider, but it's worth mentioning that we believe that the hyperwatt inverter has the widest DC input range available in the market, 90 to 600 volts. We have a very, very high quality ISO 9001 manufacturing process and a 200,000 hour MTBF, mean time between failure. It makes a 20-year warranty without replacement possible. Modularity lends the aspect of rapid replacement of the power modules in our modular inverter series. And optional heating modules are available for extremely cold climates. And we also have performance monitoring built in. Many developers consider cost per watt as they are developing a project. And it's not uncommon at all to have institutional lenders concerned about their cost per watt. we make an argument that you should really be concerned about cost per kilowatt hour, since that's really how a power generating system should be measured. And I included this snapshot of an Excel tool that we built to compare inverter performance and the impact that increased yield has on ROI and levelized cost of energy. Of course, it's important when you're deciding what type of inverter you want to use on your project to be considering these things. So this is the type of tool that we recommend you use when you're doing analysis of the yield characteristics of inverters. This schematic shows a conventional inverter with a single-stage DC to AC conversion architecture, and that's represented in orange here in the center of the diagram. Now, this conceptual diagram illustrates what's inside the hyperwatt inverter box. And you can note the 60 kilowatt DC to DC converter in yellow, preceding the 250 kilowatt DC to AC conversion step in orange. And really the heart of the difference between a hyperwatt inverter and other conventional inverters is this yellow section, although we're using the highest quality components in the balance of systems throughout the inverter. Hyperdyne's manufacturing inverters for residential, commercial, and utility applications, as you can see in the chart. We have both single-phase and three-phase products rated from 6 kilowatts up to 500 kilowatts, and in custom parallel systems greater than 500 kW. And I should also mention that above 250 kilowatts, the products are based on one or more 250 kW assemblies rather than on 12 kilowatt modules. Now let's take a quick look inside a 48 kW hyperwatt inverter pictured here on the slide. You can see there are 4 12 kW power modules arranged in the midsection of the cabinet. Those are easily removed by flipping a breaker and then undoing a set of thumb screws. And this, as I've mentioned, streamlines repair or replacement. It's the basis for our very low mean time to repair statistic. And you'll also notice at the bottom of the diagram the output isolation transformer here in the base of the cabinet. Hyperwatt inverters also include a data logger and system monitor that supports remote monitoring via the web. In addition to monitoring inverter performance, irradiance, temperature, the system can also be configured to monitor down to the level of the PV module. So in summary, a hyperwatt inverter's ability to improve electrical yield by as much as 30% translates to even larger percentage improvement in system profitability, because every additional dollar of revenue that's generated is profit. You know, as you're carrying the cost of a system, you've got whatever its encumbrance is in the terms of the cost of money, and if you incrementally increase the revenue dollars, you have a disproportionate impact on profit. So while we might see a 30% improvement in revenue, it's possible to see a 40, maybe even 50% or more increase in profit, which obviously gets stakeholders pretty excited. You have an option when you're designing a system to generate more electricity from the same number of panels, because basically you've got, two options basically. If you're using the same number of panels as you would in a conventional system, you're going to generate about 30% more energy, or you could generate an equivalent amount of energy from a fewer number of panels. And any way you look at it, this creates a situation where you've got an improved project internal rate of return, and that's obviously very attractive to all of the stakeholders. That brings me to the end of the presentation, and Rick, I would say at this point I'm happy to answer questions if we have time.
Yeah, thank you, David, and thank you for the presentation. There are several questions that have come in. Before I get started with those, if you have questions for David, please enter them into the Q&A window. The first one that I had was a question about your spreadsheet. It said, I understand how the spreadsheet can work when you enter values in, but how do you predict or estimate the efficiency improvement of a site before you purchase it or install
Right. Well, if you look at, can you still hear me okay?
Yes, I can hear you.
Great. Okay. Well, when you look at any opportunity, and we use something like PV Watts or any of the preferred software applications to go ahead and create a baseline for your system, potentially PV Watts with a D-rate or another approach. The question then becomes what can you generate with a hyperwatt inverter? Now we have experience from installations in the Northeast, which are some of the ones where we have the most impact from clouds and inclement weather, and that actually happens to be the circumstances where you're going to see the greatest benefit from a hyperwatt inverter as well. So those allow us to predict what we consider to be typical for the output of a hyperwatt inverter in those circumstances. And then, of course, if we're looking at something in the Southwest, like you saw one picture there where you've got much higher irradiance throughout the day, then the difference between the, as used in the example, a PV Watts kilowatt hour per kilowatt rating and what will generate from a hyperwatt inverter might be limited to 20 or 25% because it's now relegated more to the early morning hours and the late afternoon hours. So it's all a function of the irradiance or watts per square meter that we can actually derive from any given system at a specific latitude, and then taking the weather into account as well. And of course, based on some of the experience we've gleaned installing the inverters. And I might add that we also work with clients in what we refer to as a performance program that allows them to effectively pay for the inverter as a function of additional yield generated. So we make the device very attractive, compared in price with a competitive or conventional inverter, and then allow the yield, additional yield driven by the system to be the basis of the difference in price between the inverters.
Okay, so another question was that there are a lot of inverters in the marketplace that have a low input voltage. So compared to these low input voltage inverters, what's the difference with the Hybridyne enhanced inverter?
Well, I'm not aware of there being a lot of inverters in the market that have a low input voltage. I know that I've surveyed quite a number, and I find some as low as 250 or 285, some higher than 300 in the 330 region. But I'm not aware of any that effectively wake up at 90 volts DC. So I guess I could respond to specific circumstances if I was aware of those other inverters, but I have to say I'm not.
Okay, next question was, with the hyperwatt inverter having several more components than a standard inverter, how do you increase the reliable operating time to 40 years?
Well, the additional operating components are actually the DC to DC front end, which is a converter, which effectively takes a lower voltage, scales it up, and then provides that as an input to the second stage, which is your DC to AC conversion. The way that we create a very, very high effective life from the inverter is by the use of more expensive components. This is in some cases very close to mil spec. And we're manufacturing in an ISO 9001 environment, and everything about the inverter is designed for at the highest quality level. So it's not an inexpensive device, but I would characterize it as probably one of the best made inverters in the marketplace. So it's less about there being additional components and more about the fact that the quality of those components is higher. And as I mentioned before, we believe in a regimen of PM so that effectively we maximize the life of an inverter, and while we see that being ignored in many cases, we still see that there's a huge difference between the quality of components going into conventional inverters when compared to the hyperwatt inverter.
Okay. Next question was, what's the reason that your inverter achieves a higher efficiency under full load compared to a standard one-stage inverter? That was the in your insolation charts. I think we're talking about the yield that you showed during the sunny parts of the day, not during the cloudy parts of the day. Why would the hyperwatt inverter be superior at those times?
Well, the first thing I would say is when we look at that graph, it's not very granular. So, of course, the graph is an average of whatever the irradiance is on a second to second, well, of course, solar panels respond quicker than a second, but I'm saying if you go down to the absolute minimum time frame measured in nanoseconds and then sum that up, as those panels are fluctuating in their output voltage, what's happening is that there are periods at which the other inverter is effectively moving into a maybe off or moving into a very low range of activity with respect to its efficiency. So if you then integrate that throughout that curve, what we see is a differential between the two lines, so that the effect is that you see a much higher output from the hyperwatt inverter because it's not off and it's at high efficiency during those periods where the voltage might have dropped to 250 volts, 200 volts, 150 volts, 100 volts. The reason that we, during the period after 300 volts, which is where the other inverter typically is starting up, we're already at a high efficiency, and it's because, of course, we ramped up earlier. And then effectively, when we meet at the end, the far right of the curve, we're both at about the same point in the 96 to 97% range.
Okay, another question is, do you use electrolytic capacitors in the inverter?
We do use, as far as I understand, electrolytic capacitors. I guess from a technical component perspective, I'd have to defer the question and get back to someone on that, because I can't say that I can speak directly to the actual, devices, because I'm not an electrical engineer or the person that designed the unit.
And follow-up to that was, does your company offer a warranty or guarantee for the hyperinverter for 40 years, or even at additional cost?
We haven't been asked for a 40-year warranty. We've been asked about a 30-year warranty. We would certainly consider a 40-year warranty. And again, if the PM schedule were maintained, we wouldn't see any reason why the inverter shouldn't be capable of running for 40 years. It's a long time for the other system components as well, but if the stakeholders felt that they wanted to make an investment in a combination of solar modules, inverters, and so forth, and run that system for 40 years, we would certainly be willing to talk about a 40-year warranty.
We have some young installers in the audience, it sounds like. There was a follow-up question about the low input voltage inverters. Wanted to know if you were familiar with Power One. They have an inverter with a 90 volt minimum input for a single phase inverter.
Yeah, and that's typical. I probably should have said with respect to three-phase inverters, you're not going to find any that we're aware of at 90 volts DC. In single phase, you will find inverters that have a lower threshold. Also, you'll find competition from devices referred to as microinverters, where they're installed right on the back of the panel, and they do the DC to AC conversion at the panel level, as opposed to bringing the panels together in strings and then doing a string inverter type approach. So I stand corrected if we're talking about single phase. I apologize. There are certainly alternatives for lower DC voltage input. I'm familiar with Power One, and I suggest if you look at three-phase, you won't find a 90 volt DC input.
Oh yeah, no need to apologize. We're just trying to make sure that we get to the facts in the matter.
Absolutely.
A couple more questions. Thank you. Keep bringing these things in. One was just a little bit of housekeeping. Will a copy of this web presentation be available? We actually are recording this, and this will be converted into a video, and also the slides will be available online as well. Those will be posted in about 24 hours, and all registrants, even the people that were not able to attend, will be able to see those by logging in to the same page where they joined the webinar. Next question was another follow-up to these single-phase inverters. Wanted to ask you to compare your inverter to microinverters as far as advantages for Hybridyne compared to microinverters like Enphase.
Right. We think if you're in the single-phase category, especially now focused on the residential market, where single-phase is much more prevalent, we do see a lot of competition from microinverters, and the microinverter will also allow you to achieve increased power generation Potentially, at least we've seen numbers that state that improvement in the neighborhood of somewhere between 15 and 20%. I think you'd probably end up with a bit of bake-off then between a microinverter and a hyperwatt inverter in the single-phase category. So if we're comparing microinverter to the hyperwatt inverter on a efficacy sort of analysis, I think there'd be kind of a close race. The other considerations, I guess, to consider when you're looking at a microinverter is, number one, you're now converting DC to AC and running an AC voltage around on your rooftop. You've put a device underneath the panel on the residential roof, which means that from the perspective of a repair or replacement concern, it's not the easiest to get to, and of course it creates a situation of increased time when one looks at repairing or addressing a problem with an array that's using like an N-phase or a microinverter. If we move into a larger array, I don't see them being applied in large commercial or utility arrays. It tends not to be the prevailing wisdom to put a device on every single panel and have thousands of those inverters out in an array. It's not an efficient way to attack the problem. So in those categories, commercial and utility, we really don't see microinverters used. So it really is a case of looking at them in the single-phase application. So I'd say while we offer a product there, we find that to be a very competitive space, and we are really more focused on three-phase applications in commercial and utility today.
Okay, next question was how much efficiency do you lose to heat as the temperature goes up?
Good question. Every inverter is not just an inverter, but also the solar modules themselves are adversely impacted by heat. So the first problem is that the modules in the array will now decrease in their ability to generate power efficiency. So you're going to see a drop in voltage and current. Now, on the one hand, this isn't a bad thing from the perspective of having a hyperwatt inverter installed, because as the voltage is decreased, if it were to bridge the threshold that would cause the array the inverter in the conventional array to shut down, there is the potential that you'd have the ability to remain producing much longer with a hyperwatt inverter. But from the perspective of the actual electronics inside the inside the box, so to speak, at the inverter level, at peak heat inside the box, so you're on a 110-degree day or something like that, I think you could see potentially a percentage point or more in decrease in the conversion efficiency of the inverter, and that I think would apply pretty much to any inverter.
Okay, thank you. Looks like we have one more question, again asking a comparison question. Wanted to know if you were familiar with SatCon's Solstice solution, which is a three-phase inverter with a 50 voltage input, and the advantage of Hybridyne compared to that option.
I think what the questioner is referring to, we call a booster box approach from SatCon, and they're it's also a Canadian manufacturer, as we are. They're one of the few companies that does offer a lower threshold input voltage. I can't say specifically that I'm familiar with it being at 50. I'll take that at face value. We understand that if you look at the components required to configure the booster box configuration, it creates a very expensive solution from SatCon. So we have found it to be something where we're still competitive with a SatCon solution, but we would agree that it's one of the only ones that we're aware of in the marketplace that has a distributed, albeit not in the inverter, approach to providing a lower input voltage, higher yield inverter.
Okay, thank you. And I'll take one more question. It's about retrofitting existing installations. How easy is it if, say, a standard inverter fails to drop in your inverter and see a 30% boost in power output?
Very easy, and actually it's not a bad approach. I think with the expectation that inverters will fail typically in about 10 years after they're installed, potentially 8 to 12, so in that range. When looking at replacing an inverter, I think the plan to improve yield by 25, 30, 35% is a great one. It's very, very easy to replace an inverter when you consider it's more or less plug and play. It's terminating the inputs from the combiner boxes at the inverter. There may be a bit of a missed opportunity with respect to the way that most folks tend to over panel these days, which means that they're addressing an attempt to collect more power during a period of lesser insulation, so they actually make those strings somewhat longer to increase the voltage coming in, and then they shed the power when it exceeds 600 volts. So if that's been done, you may not be as optimally configured as you'd like to be when taking advantage of a hyperwatt inverter, because you would effectively say, well, I don't want to over panel as much, because if I shed electricity at the high end, shed power at the high end, I'm throwing it away because I am going to get it at the low end. I don't need to jigger the panel strings to try to increase my ability to derive power. I'm doing it by having the deeper, lower threshold. But yeah, it's a very good approach to plug in hyperwatt inverter into to replace a failed conventional inverter.
All right, thank you. And that's all the time we have today for questions. Again, this has been recorded, and